There we go. All right. Hi, like you said, I'm Kantrowitz. I'm here to talk about signal analysis for operations. First quick warning, this talk will involve a lot of math. The idea is to introduce you to the basic concepts and techniques in signal processing so you can use them for your operations tools in life. Let's start at the beginning. So this is a metric. It has a value at a time. You can add additional metadata to your metrics, but this is the really basic piece of what you're going to have. We can put them into, whoa. All right, we can put them into graphs. So here we have the value on the y-axis and the time on the x-axis. A thing we all look at all day, every day. So cut to the chase a little bit, this is the exact same format that your audio data is in, as well as other similar signals. So I'm sure a lot of you have seen an image that looks like this, or perhaps like this. So where do these come from? We said that audio data is similar to metrics data, but this doesn't look like a normal metrics graph. So these involve a concept called frequency domain. Previously we had a graph of value over time. Instead, those two plots are graphs of value over frequency. So this is a frequency domain or frequency space plot. So here's an example. Across the bottom, we have frequency starting at 0 hertz and going up to here 20 hertz. A hertz is 1 cycle per second. The y-axis on frequency domain plots is usually a little fuzzy. We're usually looking at relative values instead of talking about the specific absolute values on the y-axis. But you will sometimes see the y-axis denominated in decibels, usually in terms of relative decibels. That's just a compact way to represent a ratio. So saying plus 10 decibels is equivalent to saying the power went up by times 10, or you can say minus 20. That's the same as saying divided by 100. So how do we get these? We don't have frequency domain information coming into our systems. We have time domain information. The Fourier transform is the heart of most of the signal processing I'll be talking about. So it takes a time domain signal and turns it into a frequency domain signal. Here's the formal definition. This probably means about as much to you as it does to me. So let's go through this piece by piece. Start off simple. Here's a very simple graph. It's a sine wave at 1 hertz. Let's have a second sine wave. So in this case, it's a 4 hertz sine wave with half the magnitude. So this is changing 4 times as quickly, but by half as much. So let's add them together. So this is starting to look like a graph that maybe looks familiar to people, but still pretty clean. So let's add a little bit more data. Here's another graph. This is probably something that you could see walking into the office in the morning and someone saying, hey, here's a graph, what's wrong? But maybe you don't know. So what we're going to do is use the Fourier transform to convert this into frequency space and then figure out what were the original components of it. So here's what the output looks like. You can see we have 5 spikes. Obviously this was very, very periodic. Normally your Fourier transforms won't come out quite this clean, but you can see our original 1 hertz. You can see our 4 hertz at half the magnitude, so the peak is half as high. And then you can see the other components I added. But if you remember this, how many of you would have noticed that there was a 2 hertz signal in there? Kind of stuff that's very easy to miss on a noisy graph, but when you look in frequency domain, it becomes very simple. So here, for the more visual among you, you can see we have our frequency domain plot here, and you can see it's actually just 5 different sine waves broken out. So okay, so that's the basics of what the Fourier transform does. But how do we deal with this in computers? Because those little infinities are not very helpful for computers. So instead of using the normal Fourier transform, we're going to actually generally use something called the discrete Fourier transform or the discrete time Fourier transform. Instead of working on continuous signal, these work on a discrete sample signal, which is what we all have. Here's the definition of the discrete Fourier transform. So this is looking a little bit easier. If you're familiar with math, you'll know the sigma is just a fancy way of doing a sum. So this is saying for each frequency that we want to analyze, the frequency would be k, we do a sum over all of our metrics using this fancy looking formula. Only big problem with this is this means that for every frequency we want to analyze, we have to do a sum over every data point. This is order n squared time, and that's not particularly great. So instead, there's a thing called a fast Fourier transform, which is the thing you will generally use. You don't really need to concern yourself too much. It's similar to the discrete Fourier transform, but it uses a divide and conquer algorithm. So this is basically like comparing something like insertion sort to quicksort. And similarly, you go from n squared to n log n. So that's all you really need to know about what the fast Fourier transform does. And one last acronym to throw at you, IFT, or inverse Fourier transform. All this does is take all of the different periodic components, all those different sine waves, and add them back up, so you go from frequency domain back to time domain. So we have some new tools. So now we can take our incoming metrics data, which are time domain signal, we can convert them to frequency domain, and then we can do some stuff and then convert them back. So let's look at an example of a filter. This is called a low pass filter. That means that it's going to discard high frequency information. So here's our initial graph. So you can see we have a simple alert threshold there, and you can see that we are currently exceeding our alert threshold. But in Nagios terms, this would be called flapping. It's toggling on and off. You're getting paged a whole lot, and that sucks. So what we want to do is try to limit the noise that this is creating. So let's run this through a Fourier transform. We get this. So we can see there's two components here. And you can see only one of those is over the initial threshold. So if we take that red line as our frequency filter, frequency limit, for the low pass filter, so we discard everything above that on the graph. We just set it all to 0. And then we run an inverse Fourier transform, we get back this graph. So now you can see the original signal minus the event, and we're back under our alerting threshold, and we know all is well on our normal signal. So what you need here is two alerts. So you alert on both the frequency domain plot, which will be fairly static over time, usually. You won't get as much flapping in your frequency domain. So you alert on that to know that there was an event, but you don't have to alert here. So you're not passing your thresholds here, but you still need the thresholding in general for slow ramp-ups or aperiodic changes. So it's a low-pass filter. As you might imagine, you can use, you can change how you change the frequency information. So there's high-pass filter is the opposite. That's deleting low frequencies, or bandpass, where you delete everything outside of a certain range. But once you have these tools, you can do a lot of different things in the frequency space. You can change that graph in a lot of different ways. So that was a very basic explanation of filtering. Let's look at something called windowing. This is the idea of taking another signal as a mask, multiplying your signal by that function, that other signal, and using it to analyze just one piece at a time. Now, generally in operations, we can only store a finite amount of data. If you have infinite storage for your metrics, I envy you, I don't have that kind of budget. So usually we have a relatively small amount of data, maybe a few days, maybe a month. So we're always going to have a window of some kind. Before that, we don't really know what the signal was. So the problem is that this comes at a cost, something called spectral leakage. So this is the distortion of the Fourier transform of the frequency space around the edges of your window, basically. So if you have periodic components that are around the time scale of your window, that they will get very, very quickly distorted. So let's take a look at some examples of window functions. Simplest one is a rectangle. Any finite time constraint can be thought of as a rectangular window function. This is just a hard stop. At some point, you stop looking at the original signal. You can see it's zero valued everywhere except where the window is. And usually the right side would be at current time. So rectangular window functions are very nice for certain things. They have the lowest overall noise creation, but they have very high level, well, I'll show you in a second. They have very high levels of spectral broadening. So this is an example of a Fourier transform. 7 Hz sine wave over a effectively infinite length or very long rectangular window. So you can see this is exactly what we want to see. Nice smooth spike and effectively 0 or within rounding of 0 everywhere else. Problem is when you start looking at shorter time windows. So this is the same 7 Hz sine wave but with a 3/4 second window. So instead of a sharp peak, you can see we get this kind of like smooth blurring towards the edges. That's the spectral leakage setting in. So this is a diagram that shows how spectral leakage works for each type of window. There's 2 important pieces you need to look at here. So there's this main lobe up at the top, the one in the center. And you can see for a rectangular window, it is very sharp and very narrow. And that's what we want to see. That is the lobe that corresponds to our primary signal. So this means that that signal will not be what's called attenuated, which means reduced, and it won't be broadened too much. But the second feature is what's called side lobes, which is everything else. And as you can see, they are also quite high with a rectangular window. That's why we see that mushing of a peak. Very technical term. So you don't always want to use rectangular windows if you're analyzing short time spans. The next one you can look at is a triangular window. Triangular window is better than a rectangle, but not by a whole lot. So here's the same plot. You can see our main lobe again is quite tall and relatively narrow, and the side lobes are better than they were for a rectangular window. So they're reduced somewhat, but they're still pretty high. So triangular window, better, but not by a whole lot. But it's relatively simple to implement. Everyone knows what a triangle looks like. So if you want to look at a more general purpose, small value window function, this is something called a Blackman-Harris window function. I won't bore you with the details of how to derive these, but the formulas are all available on the internet. But here is what the spectral leakage graph looks like. So this is very different from the last two we saw. The main lobe, you can see, is significantly larger in terms of width, and the side lobes are significantly reduced. So what does this mean? So here's the Fourier transform of the same 7 Hertz signal, again with a 3/4 second window. The dotted line is our original rectangular window, and the one in the foreground is our Blackman-Harris. So you can see that the peak gets mushed. The signal kind of spreads into neighboring buckets, into neighboring frequencies, but it drops to 0 much faster than the rectangular window did. This is incredibly important if you're doing analysis where you don't necessarily know where your signals are and you don't want to risk them getting lost in this sort of slow bleed out to 0. So now you want to use these techniques. What are you going to do? NumPy is your best one-stop shop. It's a Python library. It integrates very, very nicely with a lot of other scientific computing tools, and it gives you a lot more numeric analysis stuff than just Fourier transforms. There's also a library called FFTW. This is written in C. It has bindings in almost every language, but those bindings are very variable quality, so caveat emptor. And if you're using Go, there's a library called Go DSP, which offers some basic Fourier transforms and windowing functions. Unfortunately, I don't know of anything for Ruby other than the FFTW binding. Ruby really doesn't have a great numeric computing community, scientific computing community, so you're kind of on your own there, sorry. So go forth and find the signal. And we have a little bit of extra time, so I'm going to skip ahead to my bonus content. So first thing in my bonus slides, discrete cosine transform. So very closely related to the Fourier transform, it uses frequency space. DCTs are the way that everything you consume is compressed. This is JPEGs, this is MP3s, this is every movie you've ever seen. It works by, you transform something into frequency space, you smooth out some of the sort of very small frequency components that are clearly not contributing greatly. So you just take the peaks, and then you write down those peaks. And then when you reconstitute the signal, you run an inverse Fourier transform, and you get back the original signal close enough. It's not going to be exactly the same, but it's within a margin of error that you can accept. And the important thing is that those frequency components can be stored in a much smaller space. This is why WAV files are much bigger than MP3s. And that's the kind of space reduction that we're talking about here, literally. So I have not found a metrics database that uses anything like DCT compression. I really, really wish someone would write one. So this is me asking you all, please, someone go write a metrics database that uses frequency space compression. A related thing to DCTs is wavelet transforms. These are similar-ish. They're at the heart of most next-generation compression systems. So H.264, for example, is using a wavelet compression system. They give you a lot of advantages with very small and aperiodic data, which again is very similar to what we work with in monitoring. So in addition to building one based around DCTs, look up wavelet transforms. Please, someone build this so I can use it. Next bonus idea I'd like to introduce, noise gates. So they're used very, very often when you're doing live audio recordings to reduce noise and crosstalk between signals. Very simply, all it means, basically, having 2 thresholds. So you have the upper threshold, the alert is activated whenever you cross the upper threshold, and is deactivated when you cross the lower threshold. So it transforms this from 4 alerts into 1, which is what you want, because who wants to get paged 4 times for this? And the general category of things, fortunately, yesterday somebody already mentioned hysteresis, so I don't need to go into too much detail on this. But it's just a fancy word for whenever the output of the system is based on the input at the current time and the output at a previous time. So we're basically just using a very simple form of memory. The algorithm knows which state it is in at any given time. That's hysteresis. And you can find a lot more interesting algorithms that use the idea of hysteresis. And finally, control theory. So if this piqued your interest in math again, another topic to read up on, control theory. Signal analysis gives you a lot of really great tools for things like anomaly detection and finding patterns. And then the question is, okay, well, I found something is wrong. What do I do about it? A great example is auto-scaling. We have great metrics for my CPU usage is really high. But then the question is, what do I do? So you want to start some more servers, but how many and when? A lot of times people will just use a simple like start one at a time, wait 30 seconds, how's my CPU usage look? And that's a very, very basic control algorithm. But we can do better. PID control loops are probably the most basic and broadly applicable control theory construct that you can use. So if that sounds interesting to you, go read up on them, or maybe I'll just come back next year and give another talk. And thank you. Time for questions? Unless I scared everybody with all of the math.
Can you demonstrate how you use the Python library? Is there too much? Or?
I can't really fit that into this talk, unfortunately. It's a little bit complicated to read up the documentation.
Are there any implementations of systems that do this with metadata?
Not that I'm aware of. I mean, my own, but not. Sorry, are there any implementations of systems using this for metric data? I've cobbled together my own. I don't know of any large-scale systems that do this. Nagios flat detection is the most terrible implementation of a low-pass filter ever because they didn't know it was a low-pass filter. Nerds do this a lot. We love to reinvent things and not pay attention to the fact that there's several thousand years of engineering history that we should all really pay attention to. I do it all the time.
You talked a little earlier about the FFT and how you had a group of frequencies that contribute to the thing you actually see on your script chart. Could you talk about an example where what are the contributors to that outcome?
Well, so I mean, most of our metrics have periodic components. The simplest one is they have a daily cycle. There'll be a frequency on once a day, it'll spike up and then it'll go down, then it'll spike up and go down. Sometimes you'll see higher periodic components, like somebody is refreshing this once a second, or you'll see 10-second components are really common because that's a socket timeout. If you start seeing those kinds of components, you know something is very wrong.
Is the system that you put together on GitHub?
No, it is not. Sorry. It's just cobbled. Sorry. The question was, is my system available on GitHub? It is cobbled together from miscellaneous Python scripts. It's not something you could really use.
I'd be surprised at what people are actually using.
That's fair. Other questions?
So if someone added like an FFT function to Graphite, would that suffice?
The question was if somebody added an FFT function to Graphite. That would be lovely. The biggest problem with doing it in Graphite is that means that you are storing all the points, which, as previously mentioned, I really wish people would stop doing. So I think that it should probably be, having some of that live in Graphite for now would be fine. I think having it be in a layer like Remon or Logstash long term would probably be better, where you're just running streaming FFT on all incoming data. One in the back that I can't see.
When you make the assumption that when you use the DSP algorithms, it makes the assumption that you're working on analog data, continuous data. Have you run into any practical problems when you pretend the discrete data to be analog and apply these algorithms?
So the question is, are there any problems pretending that these discrete systems are analog? So actually a lot of these are based around discrete systems. That's the discrete and discrete time Fourier transforms are based entirely around discrete data. The problem with audio data has always been that it can only exist in sampled form, at least as far as engineering is concerned. So all of these techniques are built for discrete data. Just, they care about very high frequency data. They're sampling at 44,000 times a second. We're generally sampling at once or twice or 4 times a second, but it's the same idea. One question?
I wonder if you know there's any kind of pink noise in the data that you want to know, which is the outcome.
Yeah, so the question is there any pink noise or other, so the colored noises, you've probably heard the term white noise before. White noise is just energy at all frequencies. I haven't really run into that much, but like I said, I've mostly been using this in cases that I knew were periodic to begin with, and I just wanted to get some analysis on that. All right, thank you very much.